We know that Kw has a value of 10 to the power of minus 14. So 10 to the power of minus 14 is equal to H plus times OH negative. So we've done this. Now we can calculate concentration of H plus by making the concentration of H plus the subject, and it will be 10 to the power of minus 14 over the concentration of OH negative. So I have the concentration of OH negative, I have the ionic product of water, so at room temperature I can calculate the concentration of H plus ions. So let me write this as Y. Then once I've calculated the concentration of H plus ions using this formula, I can put it in this equation and I can say that pH is equal to negative log 10 and Y, because Y is the concentration of H plus ions, which I've calculated using this formula. So this is how we can calculate the pH of a base, of a strong base. We will not be doing this for, we will be doing weak acids and bases later. For now, we only need to know strong acids and strong bases. So this is how we can calculate the pH of strong acids and strong bases. So now we can move forward. So weak acids, okay. So let's take for example ethanoic acid, which is CH3 COOH, and in aqueous solutions it will dissociate, partially dissociate, because this is a reversible reaction. It will partially dissociate to form CH3COO negative ions, which are ethanoate ions. CH3COO negative aqueous plus H plus aqueous ions. So this is the equation that it's a reversible reaction because ethanoic acid is a weak acid, so it will partially dissociate into ions. So in this case, what we do is that we have something called the acid dissociation constant, which is Ka, and Ka is equal to, like any other, I'm sorry for that, like any other equilibrium constant, we will first multiply the concentrations of the products. And H plus upon the concentration of the acid. So this all of these are raised to the power of 1 because their stoichiometric coefficients are 1. I can also write this as, just so that you don't get confused, this equation can also be CH3. So there are two ways of writing the same equation. One is the one I've written on top. The other one is we get the same ethanoate ions, but instead of H plus we have to write the equations are actually the same, so don't worry about that. Both of them are correct. So it's just that because we have added water to the equation, we will be writing hydronium instead of water, instead of H plus. So you see that the only difference is that when I have water on the reactant side, then instead of H plus ions I've written H3O plus ions, but that makes no difference to my acid dissociation constant. It still stays, because water is a pure liquid and a solvent in this case, so I won't